Let's talk about analyzing logistic growth using differential equations. We can model population growth with exponential growth. This differential equation dp dt equals k times p has this solution. Solution's p equals c e to the kt, in other words, exponential growth. But this is unrealistic. The population grows without limit. We know what exponential growth looks like. And nothing grows like that. Even mold on a ham sandwich that's been under your bed for a year, it's not going to grow without limits. A better model of population growth is the autonomous differential equation dp dt equals kp times 1 minus p over n. This is the logistic equation, or the Verhulst equation, after the Belgian demographer who studied it in the 1800s. Here k is the growth parameter. It's more or less the annual growth rate. We call it the intrinsic growth rate. And n is the carrying capacity, or the saturation level, or the limiting number. In other words, that's basically the maximum number of people, or maximum population that can be supported. Over time, the population approaches this number. This growth is called logistic growth. For example, the population of a particular fish in the pond at Oakden's Des Plaines campus can be modeled by the logistic equation dp dt equals 0.05 p times 1 minus p over 300, with initial value p of 0 equals 100, where time is measured in years. A, how many fish are in the pond in the long run? Okay, method 1. We can graph this using a slope field plotter like GeoGebra. Let's go ahead and enter that. So you enter y prime, you just find slope field plotter or slope field generator using a search engine. You enter the differential equation, choose some nice bounds. You might have to play with those a little bit, and you end up with something that looks like this. You'll also have to enter the you'd also have to enter the initial value, namely p of 0 equals 100. You get something that looks like this. I did this using GeoGebra. And the limiting population, the maximum population, seems to be 300 fish. That's what we end up with in the long run. Okay, method 2. With the logistic equation, the population in the long run is also an equilibrium solution. We know how to find equilibrium solutions. We take this side of the differential equation and set it equal to 0. When we do that, we end up with either 0.5p equals 0 or 1 minus p over 300 equals 0. This leads to p equals 0. That's an equilibrium solution. If you start with no fish, it just stays with no fish forever. Or this is another equilibrium solution. That's really the one we're looking for. P equals 300 fish. Let's solve the initial value problem. dp dt equals 0.05p times 1 minus p over 300. P of 0 equals 100. This logistic equation is a separable differential equation, which is cool. We know how to solve those. And if you were to go through the process of solving this separable differential equation, you'd end up with this as a solution. So p of t equals p0 n e to the kt n over all over n minus p0 plus p0 e to the kt. Now, for this differential equation, we have k equals 0.05, n equals 300, and p0 equals 100. We saw that. So this solution, p of t, ends up looking like this. We have 100, that's p0, times n, that's 300, times e to the kt, that's e to the 0.05t, all over n, which is 300, minus p0, so that's minus 100, plus p0 e to the kt. In other words, 100 e to the 0.05t. All I'm doing is plugging these numbers into our solution. And when we simplify it, we end up with 30,000 e to the 0.05t all over 200 plus 100 e to the 0.05t. So that's our solution. So suppose we're simply told that we have logistic growth with, again, this differential equation, an initial population of 100, a limiting population of 300, and p of 12 equals 143. So in other words, we're not told what k is, and we're asked to find p of t. So here's what we do. We know the formula for p of t. We plug in what we do know. We don't know k, so we can't plug that in, and we just end up with this over here. We find k by plugging in t equals 12, because we know the population at time t equals 12 years. So here's our solution. So plug in t equals 12. We end up with this equals 143, because we know the population at time t equals 12 years is 143 fish. By solving this on a graphing calculator, there are different ways we can do it, we find that k is about 0.04998, or in other words, around 0.05. So we end up with the solution we had earlier. P of t equals 30,000 e to the 0.05 over 200 plus 100 e to the 0.05t. Okay, the population of the United States in the last 3 censuses are given in this table. So we have the 2000, 2010, and 2020 populations. Construct a logistic population model using the data from 2000, 2010, and 2020. Assume that T is years since 1790 is P, and P is the population of millions. Okay, we're going to use the TI. Use your TI to solve this problem. So first, let's represent these years not as 2000, 2010, or as 2020, but as years since 1790, because that's where we're told. T is years since 1790. Okay, on a TI-83 or 84, press Stat, choose Edit. Edit is over here. Yeah, so here's Stat, choose Edit, and then press, and then this Edit, and then press Enter. So we end up with this screen. Enter the data in columns L1 and L2. If you already have data in those columns, then go to the top, L1, and press Clear, and then Enter, and that'll clear the data out of the columns. So you enter the data into the columns, 210, 220, 230, and then those populations, and press Quit. Second in mode. Quit is second and then mode. Okay, next we press Stat, choose Calc, not Edit this time, but choose Calc, and then Logistic, and press Enter. You should end up with a screen that looks like this. Press Enter again, and it will give you the answer after a few seconds. This is so cool. This takes so much less time than doing it by hand. So this is your answer. So here's the way we interpret this. It tells us what y is. The formula looks like this. That's the solution to the logistic equation. And it tells us the values of a, b, and c. So in other words, y is c over 1 plus a e to the negative bx, where these are the values of a, b, and c. So in other words, plugging in a, b, and c, we end up with this. Okay, now use the model to predict the U.S. population in 2030. We've got this as our predicted population in year t. Let's switch everything to t's instead of p's and instead of y's and x's. So we have p of t looks like this. 2030 corresponds to t equals 240 years after 1790. So p of t40 looks like this. And when you plug that into your calculator, you end up with 349.6. So that's our answer, 349.6 million people. We should always ask ourselves if our answer is reasonable. Yes, that's a reasonable number of people for 2030. That seems reasonable.